All right, so let's talk about what polarity is first off when we're thinking about it as a definition. So when we're talking about polarity, we're talking about a molecule's overall charge. There are two choices when it comes to polarity. The first one is a molecule will be nonpolar, which means that the molecule has no charge. Or a molecule could be polar, which means that it has a slight negative and a slight positive end. Someone at the door?
I'm so sorry to interrupt you, but I'm looking for one of my students misplaced their algebra book, and it might be in the class.
Ooh, I thought I saw something. Did you guys? I see it. Got it.
Thank you for being here.
All right. So, slight positive, slight negative end. It's important to note when we are talking about this that it is not the same as being like positively charged or negatively charged. It's only very slightly. So it's not as strong as like an ionic kind of charged particle. So the example that I have for you guys is the water molecule, which we talk about a lot when we're talking about solubility. So that's just what a molecule of water would look like. It's oxygen with two hydrogens attached to it. And the oxygen end of it is slightly negative. That little weird kind of D symbol is how we annotate for something that's being slightly. So slightly negative, and then the hydrogen end is slightly positive. So that's what a polar molecule would look like. And don't worry, I'll explain how we decide what we have. All right, we okay so far? Shall I keep going? Okay. So, two steps you guys have to make in order to make this decision. The first step, so step number one, is that we need to decide if the bonds in the molecule are polar or nonpolar. When we are deciding if a bond is polar or nonpolar, we're basically asking, are the shared electrons involved in the covalent bond being shared equally? I should say, are the molecule's shared electrons being shared equally? So that's our first question that we are asking when we're looking at this. If the answer is yes, they are being shared equally, well, then we call that a non-polar covalent bond. Now, it's going to be quite confusing because I'm going to be using the terms, are the molecules shared electrons being shared equally? So if the answer is yes, then what we're going to call that is a non-polar covalent bond. Unfortunately, we're going to use the term non-polar and polar for both describing the bond and describing the molecule. So be careful when you answer which one you are referring to. It's useful to write bond or molecule or overall when you're trying to explain which one's which. If the answer is no, then we have a polar covalent bond. And I will pass out your next set of notes. which is a nice little resource to help us decide which one's which. Yeah, I can't see it.
You have to know rhyme or reason for both my colors, you know that, right? Okay. Sometimes my color would things other times I just came up with random art.
Okay. So the way we decide if these electrons are going to be shared. Anyway, the way we decide whether or not these electrons are going to be shared equally is by using something called electron negativity. Electron negativity is just referring to the attraction between the nucleus and the shared electrons. Do you want me to write that down? Okay. Yeah. Okay. So this is decided by the electron negativity. Oops. So electron negativity, we are referring to the attraction between the nucleus and the valence electrons. So what I've given everybody is this little periodic table. It's slightly different from the other periodic tables that you've been given because this is an electron negativity periodic table. Unfortunately, they do not give this to you on the exam. Do not memorize these numbers. It wouldn't be a useful use of your brain space. The main thing I'm just kind of using this for is to kind of teach you when different bonds occur. So when we are looking at this, the most electron negative elements are the ones that are really, really dark. For example, fluorine, and unfortunately the photocopying made it really dark and almost unreadable, is the most electron negative element, and that one has the value of 4. The least kind of electron negative elements that we're looking for are on this group number 1. You can see that it can be as small as like 0.7, I believe is the smallest one we got. Now, when we're thinking about electron negativity, the most electron negative element, like okay, sorry. Okay, so the most electron negative element is going to be fluorine. When we think about this as a concept with this atomic structure, fluorine has 7 valence electrons. If it just gains 1 more, it'll be stable. Group number 1, those elements there have 1 valence electron. If they just lose that 1 valence electron, they will be stable. So we can use that as an idea to help understand how, quote unquote, much the atoms want another electron. If they can easily gain a few electrons and then become stable, their electron negativities are going to be much higher. If they can lose an electron and become stable, their electron negativities are much lower. So that's the tie-in with that. The other thing that I want you guys to keep in mind is that when we are talking about these various bonds, it's more like a continuum than a set categories of stuff. So with the difference in electron negativities, that can help us decide what type of bond is going to be occurring and why. So if we had a nonpolar bond, what that tells me is that the difference between the two elements on the periodic table is very small, and so neither of those two atoms would have a stronger pull on those 2 electrons. As a rough kind of estimate, the nonpolar elements, or sorry, I should say nonpolar covalent bonds, is a difference of about 0 to 0.4. It's a rough guideline. So if the difference between these two numbers is very minor, it'll be a nonpolar bond. If it is a polar covalent bond, then what's going to happen is my electrons will be shared, but they'll be shared a bit unequally, and it'll be closer to the atom that has the greater electron negativity. This happens roughly between 0.4 and 2. So between that range of a difference, I would expect my elements to have a covalent polar bond. And then the last bond that we are thinking about is that ionic bond. So that's the full transfer of the electrons from one atom to another atom, forming ions. That difference is anything above 2. So if the difference between the two atoms is greater than 2, you should expect something that's going to form an ionic bond. So like, for example, when we're looking at things, we often see things like sodium being paired with chlorine to form sodium chloride. Chlorine has an electron negativity of 3, and sodium has an electron negativity of 0.9. So if we do the subtraction difference, that would be 2.1, and that is greater than 2, so that's why that one forms an ionic bond. Whereas if we're thinking about things like oxygen and carbon, that's 3.5 and 2.5. If I subtract those two numbers from each other, I get 1. And so carbon and oxygen are then more likely to form a covalent bond and share those electrons because their electron negativity isn't great enough to pull one off. So I figured that was worth explaining just because it helps kind of cement the types of solids information. Are we okay with that so far? All right. So some things to keep in mind. Terminology is really important when it comes to this question, and just be careful when you are writing your answers. When you are commenting on polar and nonpolar, you can only use that reference when we're talking about covalent bonds. If you are talking about ions, you refer to them as being charged particles. So basically what I'm trying to get you guys to be careful of is if you're talking about ions and you're saying, oh, the sodium is polar, or the sodium ion is polar, I would mark you as incorrect because that is not the correct way to describe an ion. You should be describing it as a charged particle or positively charged particle. When you're talking about molecules, you shouldn't say that they're positively charged or negatively charged. You should be talking about them as being polar or nonpolar. Just watch that terminology. It really affects people that are trying to aim for excellence, because if you're not using the correct terminology, that shows me you're not an excellent level student. All right, so that is the first deciding factor. The second deciding factor of whether or not something's going to be polar or nonpolar is going to have to do with the shape of the molecule. So number 2, does the shape allow symmetry? So what we're trying to basically be thinking about is, do I have symmetry in the molecule that's going to result in the slight charges canceling out? So for example, if I was thinking about methane, which is my single carbon attached to 4 hydrogens. If we looked at the electron negativity table, I can see that carbon is 2.5 and hydrogen's 2.1. So there's roughly a 0.4 difference. So enough that it might make a slight polar bond. Are we okay with that? So slightly polar with the carbon pulling the electron slightly closer to it. So the way I would annotate that would be I would have these little arrows. And I'm putting these little like positive signs because what I'm trying to explain when I'm doing that image is that the carbon is pulling those electrons closer to it, making it slightly negative. And then the hydrogens, because they don't have those electrons as close to them, they're going to be slightly positive, like that. Now, when I look at this molecule, there is symmetry, and I will notice that the positive charges are going to cancel out. So like charges cancel out if there's symmetry. And since these charges are canceling out, this molecule will end up being nonpolar. I can show you another example of stuff that would be polar. Keep going. Okay. Let's say I have the exact same molecule, but I switch one of those hydrogens out for chlorine, like that. In this molecule, if I look at the chlorine versus the carbon, the chlorine is more electron negative. So this guy's going to pull the electrons closer to it. Carbon will still pull these these shared electrons closer to it. And so what I will see is that my chlorine will be slightly negative and the hydrogen will be slightly positive. In this case, when I look at the charges, I have these two positives on one side, but on this side, I have a positive and negative, so they're not going to cancel out. So since there's a lack of symmetry, this will be polar. Would you guys like some more examples? Just to know what you're looking for? All right, I can do water, which we've talked about before. Actually, I'll draw it like that. So when I'm looking at water, I can see that first off, oxygen is slightly, it's more electron negative, so it's going to pull those electrons closer to it, leaving my hydrogen slightly positive. And on top of that, the oxygen has lone pairs of electrons, so that's going to also accumulate to cause it to be very negative on that end. And then on the opposite end, with my hydrogens, they're going to be slightly positive. So that molecule is polar. Let's look at another one like carbon dioxide. So we know that the oxygens are more electronegative than the carbon. When I look at that, it's the difference between 3.5 and 2.5. But in this case, the negative ends are on opposite sides, and it's the same charge. So those will cancel out. And so that one will be nonpolar. All right. I'll give you one more molecule because I'm going to prove one more point. Let's talk about the do now. All right. When you're looking at that molecule, oxygen's more electronegative than sulfur. So we would expect the oxygens to be negative, but we'd also be mindful that the sulfur has lone pairs of electrons up there too. So you see how we have negative all around? The thing we have to remember, though, is that the negativity caused by lone pairs of electrons versus bonded pairs of electrons is different. So this is not an even negative distribution. So it's not an even kind of negativity. So in this case, it doesn't cancel, and it'll be polar, this one here. So I just want to point that one out. Oh my goodness. Right. I know, lots of interruptions today. Does that hopefully make sense to you guys? Yeah? All right. I figured it'd be nice to have a little break and for us to play a little game. I want to play last person standing. Okay? I'm going to pause the video because we probably don't need that recorded. All right. Okay. So, one of the other things that we talked about for this, or that we need to talk about for this lesson, is solubility. That's going to fall under your types of solid question. And some of you guys were having a hard time answering that last week on the quiz. And I said, don't worry. When we do polarity, this will make more sense because now we actually understand what we're talking about when we talk about water being polar and how does that influence things being able to dissolve. So, just kind of walk you through this video. It's a really good animation of salt dissolving in water. So here's my little water molecule that we talked about earlier. And then that is my 3D lattice of sodium chloride, my salt. So that's an ionic solid. And as we were talking about today, water is a polar molecule. So the oxygen N is going to be slightly negative and the hydrogen N is going to be slightly positive. Sodium chloride is a charged ionic substance. Sodium ion is positive because it's lost electrons, and the chloride ion is negative because it has gained electrons. And what happens when salt dissolves into water is that these water molecules are pulling these ions apart from the 3D lattice and isolating it. And then opposite charges attract. Let me just pause it there so you guys can see it. So, chloride ion, negative. The positive sections of the water molecule is isolating it. Sodium ion, positive. The negative sections of water is isolating it. So that's how it's causing it to dissolve. Like that. And that's how that's how water is able to dissolve something like an ionic salt. Now, I noticed some of you guys on the quiz were using the solubility rules to try to explain whether or not something was going to be soluble. And that is correct when you guys are thinking about it. The thing is, on this assessment, the ionic solid that they'll give you is most likely going to be a soluble one because they're going to want you to be able to explain why it's soluble. So you don't have to worry about the solubility rules when it comes to this question. The other thing is that they're not going to give you the solubility rules on the exam. So just kind of keep that in mind. So what else did I want to talk about with the notes? Yes. So when you guys are thinking about solubility, let's move back to the notes. I'll keep this nice and short. You guys have time to work. All right. So when you guys are talking about solubility and your justifications, what you need to really think about is the attraction that the solid has to itself versus the attraction to the solvent. Attraction to itself versus the solvent. If the self-attractions is greater than the solvent, then it won't dissolve. And if the attractions to the solvent is greater, then it will dissolve. Now, when we are talking about the solvent could be something that is polar or non-polar, and that does influence the answer. So polar, most commonly, if they give you something that's polar, they'll give you water. or it could be something that's nonpolar. So I'll just make a quick little table for you guys. So with the types of solids, we had the ionic solid. And we're thinking about it if it's in water versus a nonpolar solvent. So ionic solids will dissolve in water because we know that water has that slight positive and negative charge that will isolate the charged ions in a ionic solid. In a nonpolar solvent, it would not dissolve. So if you want to try this at home, you can try to take salt and dissolve it into oil, and it's not going to do it. Yeah? Next one we have are the metals. Metals won't dissolve in either. The metal bonds are too strong that the water molecule won't be able to break them apart. What's the other one that we had? Covalent networks. For a covalent network, neither of them will be able to dissolve a covalent network. Those covalent bonds are really, really strong. And then lastly, the covalent molecules. If the molecule is polar, it will dissolve in water. It will not dissolve in a nonpolar. And if the molecule is nonpolar, it won't dissolve in water. It will dissolve in a nonpolar solvent. The way that you can remember this is like with like. So if they're both polar, they will dissolve into each other. If they're both nonpolar, they will dissolve into each other. But if you mix a polar and a nonpolar together, they won't dissolve into each other. The example I have is water and oil. Those two are both covalent moleculars, but they do not mix. Question? You want me to go up? Actually, do you want me just to zoom out? Right up? Now you can see everything. So that's like my little table. Look at my wire. There you go. Cool. Questions, concerns, comments? Just watching the time because I want to make sure you guys have time to do some work too. All right, I'll just pause the recording.